Hi, Year 12s. In the last lesson, we started looking at the concept of free energy for chemical reactions. And we met this very important equation here, delta G equals delta H minus T delta S. As you know, this delta G here is referred to as Gibbs free energy. And it's described as the energy available to do work. If you're interested to know more about that, perhaps you might like to look up Josiah Willard Gibbs and find out a little bit about him and his original descriptions of this term. But anyway, that's by the by. Most importantly, though, we met this equation. So Gibbs free energy, delta G, is delta H minus T delta S, where delta H is the enthalpy change for the chemical reaction of a system, and delta S is the entropy change for the chemical reaction of the system. And the free energy is the consequence of those two things together and how they interact with each other. So we have already looked through the derivation of the equation, which was contained in the first PowerPoint. And scrolling on down, we've also started looking through the second PowerPoint, which was this one. Now, the very last slide of this PowerPoint, which is 17 slides long, is this one. And I would like to give you a short screencast today, just to explain the importance, the usefulness of this particular PowerPoint slide that you're looking at here. Okay, so back to basics. If a reaction is to be spontaneous, the sign of delta G must be, you should be thinking now, should it be positive or negative? The correct answer is, of course, delta G must be negative for a spontaneous process to occur. Why? Because if you remember the meaning of this term, delta G, it was the negative of the temperature multiplied by the entropy change of the universe. And the entropy change of the universe, according to the second law of thermodynamics, must be positive. So if this is the negative of the entropy of the universe, this has to be negative for it to be a spontaneous process. Now, what we're looking at here is what will allow delta G to be negative. What will allow delta G to be negative? In other words, what will allow a process to be spontaneous? So we're predicting spontaneity here. We're going to reason it based on the interplay of the two terms that's within this equation. One is the delta H term, and the other is the negative temperature times the delta S term. And it's the interplay of this delta H and the negative T delta S which will determine the sign of delta G overall. Perhaps it would be better if I said it would be the magnitude of delta H compared to the magnitude of negative T delta S, which will determine whether delta G is negative overall. So let's look at a few scenarios. So the first scenario is delta H for the chemical reaction is negative. Yeah. So we're talking about an exothermic chemical reaction. We're talking about an exothermic chemical reaction whose entropy change is positive. And remember, that's also a favorable thing. Positive entropy change means increasing disorder, if you like. So not only is the reaction exothermic, but it's also one that's expanding. There's an increase in disorder. Okay, so if delta S is positive, then the negative of the temperature times delta S is, of course, going to give a negative value, which is here. So in this first scenario, delta H is negative. Negative T delta S here, this value is also negative. So if this is negative and this is negative, then whatever way you look at it, delta G is going to have to be negative. So in other words, it will be spontaneous under all conditions, spontaneous at all temperatures. Okay, that's one scenario. If it's an endothermic reaction, if delta H is positive, now that's not looking favourable. And also, the entropy change is negative. That means a decreasing disorder. That is also unfavourable. It's not only is it endothermic, but also there's a decrease in entropy. Now, neither of those things is favourable. Let's just see how it works up here, though. If the entropy change is negative, then the negative entropy change will give a positive value. So delta H, positive. Negative T delta S, also positive. If this is positive, and this is positive, whatever way you look at it, delta G is going to end up being positive. This will not occur. This is what we call non-spontaneous at all temperatures. Okay, other possible scenarios that might be more successful in terms of allowing a process to be favourable or spontaneous. Suppose it's an endothermic reaction, but accompanying it is a large increase in disorder. It has a positive entropy change. So, for example, this could be a barium hydroxide with ammonium chloride, the classic freezing water experiment. So it's very endothermic, but it's also a large increase in entropy when it occurs. So if delta S is going to be positive, the negative of the entropy is going to give a negative value. So now we're looking at situations where delta H here is positive, but this is negative. Now, provided that the magnitude of this negative value is bigger than the magnitude of this positive value, then it will be negative overall. To make the magnitude of this negative value sufficiently large, we need a large temperature value here. So at high temperatures, the negative of delta S here is going to give us a large negative number. So this will be spontaneous at high temperatures, but non-spontaneous at low temperatures. So it may or may not be a spontaneous reaction, depends on how high or low the temperature is. So, for example, delta H is positive. If we have a low temperature here, a small number for T, then the temperature value times delta S is going to give us a small negative number here. And if the small negative number is smaller than the positive value, it's still going to be positive overall. So it will be non-spontaneous with a low T value. So temperature favours this type of situation. But the final possibility is this one. Delta H, negative, exothermic, that's favourable in terms of energy. However, delta S is negative, meaning it is a decrease in entropy as the reaction occurs, a decreasing level of disorder. That is unfavourable. So what's that going to do to the minus T delta S? Well, if delta S is negative, minus T delta S is now going to be positive. So we're looking at situations here where this value here is negative, which is going to assist delta G being negative, but this term here is going to be positive, this one. And again, if it's going to be spontaneous, we need the magnitude of the negative delta H to be larger than the magnitude of the positive value here. If this value here becomes too positive, then it will balance out the negative value for delta H and it'll become positive overall. So in this case, we want to make sure we keep this value here low. We want a small minus T delta S. So we want a low temperature value here. So at low temperatures, small value of T minus T delta S is going to give us a small positive number. And provided that it's smaller than the magnitude of the negative number here, it can still be negative overall. So at low temperatures, we would still end up with a negative delta G, and it would be spontaneous. Now, why am I showing you this? Because very simply, it's a common idea that you will need to use to answer exam questions. You're going to see, and I'm going to share some with you today, some very common exam style questions. They will ask you, is this particular chemical reaction spontaneous at a particular temperature? And you can plug in the temperature values into this equation to see if you get a positive or negative delta G. And then the question will ask you, what will happen to the spontaneity as the temperature is increased or decreased? Will it become more or less spontaneous? And it will depend upon the magnitude of these two terms. So please rewatch this if necessary, and I will be sharing some questions with you for you to try. You'll need to be using these ideas. Okay, thanks very much, folks. Hope that was useful.